laminar flow through a circular pipe. So now say we consider a circular pipe. So this is a circular pipe with us. Okay. Now this is the direction of flow. Okay. Now I consider a small cylindrical element in this. So this is a very small cylindrical element within the pipe. Okay. Now say the length of the cylindrical element is dx. Okay. The radius of the cylindrical element is r, small r. Okay. Now we measure the distance y from the pipe walls. The distance y we measure from the pipe walls. So say we have this distance is y. Okay. Then the pressure intensities. So we write the forces on this element. So for forces we consider the pressure force and the resistance force only. Okay. So for pressure force you have to see the pressure intensities. So say here the pressure intensity is P. On this phase the pressure intensity is variation along x-axis. So P plus curly P by curly x dx. Okay. And along the surface, okay, along the surface of this pipe we have the you can say shear stress, that is tau. So with the help of these two you can find out pressure force, net pressure force acting on this element, as well as the resistance force acting on this element. Okay. So now I write first the pressure force acting on this element. So the pressure force is, so say we find out along the direction of flow. Okay, we find out along the direction of flow. So I can write it as P into area. Now area of the element. Now radius is r, small r. So area I can write as pi r square. Okay. So this force in this direction opposite to flow. So minus P plus curly P by curly x dx into the area pi r square. Okay. Then the resistance force. So resistance force is due to this tau. So again it is in the direction opposite to flow. So minus tau into the surface area of this element. The surface area is 2 pi r into the length dx. Okay. If only these two forces are acting, so sum of these two forces must be equal to 0, or these two forces must be equal. Okay. So from here I can find out sum जो है वो cancel हो जाएगी इसमें. So we left with minus of curly P by curly x dx into the area pi r square, or minus 2 pi r into tau into dx equal to 0. Okay. Now I divide all these terms by volume of the element. So the volume is area into the length. So I divide all these terms by volume. So volume is area into dx. So we have the resulting relation now. The first is ये cancel हो जाएगी term. So first term is minus of curly P by curly x. This is equal to यहाँ पे आपके पास बचेगा minus of 2 tau by r. No, not minus. ठीक है. और I can write it as curly P by curly x equal to minus of 2 tau by r. Okay. Now say this is equation number 1. Okay. Now the value of tau we can write from Newton's law of viscosity. So tau I can write as mu du by dy. Okay. Tau is mu du by dy. Now you see this diagram. Okay. Now what is the relationship between y and r? The relationship between y and r. If we increase y, r decreases. ठीक है. अगर आप y इंक्रीज कर रहे हो तो r जो है वो डिक्रीज होगा. अगर आप स्मॉल r इंक्रीज कर रहे हो तो y जो है वो डिक्रीज होगा. That means there is a opposite relation between y and r. So I can also write this relation if I want to write this du by dy in terms of radius of the element. So I can write it as minus of mu du by dr. So tau I can write as minus mu du by dr. So the extra minus sign, this is because of the opposite relation between y and r. So we can again write the equation number 1. So equation number 1 I can write as so before writing equation number 1, I do one thing more to this relation. I say that the variation of pressure is only along x-axis and variation in tau is along y-axis. So that means P is independent of y and tau is independent of x. So I can write the equation 1 again with exact derivatives. So I can write it as dp by dx also equal to minus 2 tau by r. So now I put here the value of tau. So this comes out to be dp by dx equal to, this is 2. Okay, this comes out to be 2 mu by r du by dr. This is your equation number 2 now. Okay, so this is the relationship between pressure gradient and velocity gradient. Equation number 2 is a relationship between pressure gradient and velocity gradient. So equation number 2 now we use to find out the velocity profile along this section. Okay, so to find out the velocity distribution, okay, so what I can do now, I can integrate equation number 2 with respect to r. Okay, so from here equation number 2 I can write du by dr equal to 2r, sorry, it is not 2, I can write it as r divided by 2 mu dp by dx. Now I integrate with respect to r, so take this dr on other side over here. Okay, integrate. So this comes out to be u equal to 1 upon 4 mu dp by dx. Okay, so here is r, so it is r square by 2, so 2 into 2 becomes 4 plus a constant c1 or c. Okay, so after integrating this equation with respect to r, we have this relation now. Now we have to find out the value of constant c. We have to find out now by using the boundary condition. The boundary conditions are, now say the total radius of the pipe is r. This is capital R. Capital R is the radius of the pipe. So that means if R becomes equal to capital R, okay, that is at the pipe wall, the velocity of flow is 0. The velocity of layer which is just touching the pipe is 0. So R equal to capital R, U equal to 0. This boundary relation I use to find out constant C. Okay, so by putting this value of R and U, the constant C comes out to be minus 1 by 4 mu dp by dx. So change R with capital R, that is R square. So this is constant C by putting this boundary condition. Okay, now I again write U by putting the value of C over here. Okay, so U comes out to be, so 1 upon 4 mu, take negative sign with pressure gradient because pressure drops along x-axis, okay, into R square minus R square. Okay, so this is equation number 3. Now you can see this equation again. U is depending on square of R. So that means this variation again is parabolic in nature. Okay, so if I draw the velocity profile, okay, this is parabolic in nature. This is how velocity varies along the section. So now I find out where this velocity is maximum. So for that you can see the profile U, velocity profile. So to find out where this velocity is maximum, so to find out maximum velocity, I put du by dr to 0. Okay, you can derivate this relation. So du by dr, I can write it as 1 upon 4 mu minus dp by dx. Okay, so I have to differentiate only this term. So r is constant, capital R is constant. Okay, so so the differentiation of constant term is 0. So then for r square, I can write it as minus of 2r. Okay, so I differentiate equation 3 with respect to r. So I have this relation now. Okay, now put this equal to 0. So that means either this term is 0 or this term is 0. So the pressure drop cannot be 0, mu cannot be 0. So therefore, R should be equal to 0 for maximum velocity. That is along the center of the pipe, along the axis of the pipe. So you can say the velocity is maximum along the central axis of the pipe. Okay, so you have V maximum along the center. Okay, now you can find out the formula for Vmax. Okay, you can find out the formula for Vmax from equation number 3. So U becomes equal to Vmax. U becomes Vmax when R equal to 0. 4 mu minus dp by dx into R square. This is equation number 4. Okay. Now, if you see equation number 3 and equation number 4 again. Okay, equation number 3 and equation number 4 again, I can write U again in our form. You can see 1 upon 4 mu in this equation, 1 upon 4 mu minus of dp by dx or R square. Okay, this becomes Vmax. Okay, this becomes Vmax as equation number 4. So I can write equation 3 again as Vmax into 1 minus small r upon capital R square. So from this part, I take R square, capital R square out. Okay, तो जो बाहर टर्म आपके पास आएगी, that is the Vmax. So within bracket you have 1 minus small r upon capital R square. So this equation is another form of velocity profile, or you can represent the velocity profile in a circular pipe. So U equal to Vmax 1 minus small r divided by capital R square. Okay. Then next I have to find out the average velocity. Average velocity. So average velocity is discharge through the pipe divided by area of the pipe. Area of the pipe is pi r square. So now I have to find out discharge. पहले discharge find out करेंगे, then V average. So to find out discharge, I have to find out the small discharge. So for that, if I draw a cross section of the pipe that is circular, this is a cross section of the pipe. Okay. So along this cross section, I consider a small ring. Okay. This ring is at radius r. Okay. Having thickness dr. So capital R is the radius of the pipe. Okay. So I consider this small ring. So now water enters through this small ring in a plane perpendicular to your screen now. Okay. So that water enters with velocity, say u. Water enters to this small ring with a velocity small u. Now I write the small discharge entering through this ring, small ring. So discharge I can write as area of the ring multiplied by the velocity of flow through the ring. So the area of the ring is 2 pi r into thickness dr into the velocity, that is u. Okay, 2 pi r into the thickness of the ring dr, that is the area of the ring, multiplied by the velocity of flow through the ring, that is u. Okay, so now I put here the value of u. So 2 pi r into dr. So u I have equation number 3. Okay, so from equation number 3, I can write it as minus 1 upon 4 mu. Sorry, 1 upon 4 mu. 1 upon 4 mu minus of dp dx into r square minus r square. R square minus small r square. Okay, this is not small dq. So dq is the small discharge entering through the ring. So now I find out the total discharge q, that is the integration of dq. The limits are now from when small r varies from
0 to R.
0 to
Capital.
capital R. Okay, capital R. Okay, so now I integrate this relation and put the limits 0 to capital R. So I write it again. 2 pi r constant, that is outside, r square minus r square divided by 4 mu. Okay, then minus of dp by dx. Then we have take 2 pi out only, so r to integrate hoga. Okay, so within integration you have r into dr. So the limits are 0 to capital. Okay, so now you find out the integration. So I write the resulting equation as q is equal to pi r raised to power 4 divided by 8 mu minus dp by dx. So this is the formula for discharge through the circular pipe. Okay, so now you can easily find out V average. So Q divided by area, pi r square. So the formula for average velocity comes out to be 1 upon 8 mu minus dp by dx into r square. Okay, that is equation number 5. Okay, so equation number 5 is the relation for average velocity. Then next you find out the ratio of V average to V max. Now for circular pipe, you can see equation number 4 for V max. Okay, and equation number 5 for V average. So divide 5 equation with 4. You see this ratio is 1 by 2. Okay, so here you have V max in equation number 4. Okay, and V average in equation number 5. When you divide both equations, V average to V max, this ratio comes out to be 1 by 2. Okay. Now here we find out one more additional thing. Now we have this circular pipe. Okay, the velocity variation is parabolic in nature. Okay, so at the center, the velocity is V max. Along the walls, velocity is 0. Okay, so along y direction, we have one layer. We have one layer whose velocity is equal to V average. Okay, we have one layer whose velocity is equal to one layer because velocity varies from 0 to V max. तो एक layer ऐसी आएगी that is in the form of a circle. ठीक है, अगर हम क्रॉस सेक्शन की बात करेंगे that is in the form of a circle. ठीक है, along this circle when flow enters, the velocity is equal to V average. So now we have to find out that radius r. So we have to find out radius r for the layer whose velocity becomes equal to V average. Okay, so now you can find out from this value u equal to, you have relation V max
into 1 minus R by
into 1 minus R upon capital R square. ठीक है, relation for V average to V max is, if you put this value of V average, that is V max by 2. that is Vmax by 2. So this term should be equal to Vmax by 2.
Sir, capital R by root
So
2.
Vmax जो है वो Vmax से कैंसिल हो जाएगा, ठीक है, हाँ कुछ इस तरह से आएगा. तो जो रिलेशन अब आपके पास आएगी, फाइंड आउट फॉर R एंड कैपिटल R, सो इट कम्स आउट टू बी 0.707. ठीक है, तो इसका मतलब है कि इस रेडियस पे, ठीक है, द वेलोसिटी ऑफ लेयर इज V एवरेज, सॉरी V मैक्स V एवरेज, द वेलोसिटी ऑफ लेयर इज V एवरेज. Okay, then find out shear stress variation. Okay, so to find out shear stress variation, use equation number 1. So from equation number 1 we can write tau R by 2 minus dp by dx. So you have this equation number 1, this one. Okay, so from equation number 1 write tau. So tau comes out to be R by 2, small r by 2, within bracket minus of dp by dx. So you see now the variation of tau with respect to R is linear nature. Okay, tau is 0 when R is 0. So tau is 0, R is 0 when this is along the axis of the pipe. This is along the axis of the pipe. So along the axis of pipe, velocity is maximum. So there is tau 0. Okay. So when tau is maximum, so tau is maximum when R is maximum, small r is maximum. So the maximum value of R is at that very time you have maximum. That is along the pipe walls. So the tau max you can write as R by 2 minus of dp by dx. This is the maximum shear stress we have. Okay. Then the last, we have to find out the pressure drop. So last we have to find out the pressure drop. Now again this pressure drop in terms of V average velocity. So for that you use the relation for average velocity. So that is your equation number 5. So from equation number 5, I can write minus of dp by dx. Minus of dp by dx. So this comes out to be equation number 5. Minus of dp by dx, V average into 8 mu divided by R square. So it comes out to be 8 mu V average divided by R square. Okay. Now again you consider 2 points. So this is a circular pipe we have. This is the circular pipe. This is the reference section. We consider say point 1. We consider point 2. Point 1 is at distance x1. Point 2 is at distance x2. So the length between these 2 points becomes L. At point 1 pressure intensity P1. At point 2 pressure intensity P2. Okay. So now from this summation you can write minus of dp as P1 minus P2. Okay. 8 mu V average upon R square. So here you have dx on other side. So dx is x2 minus x1. Okay. So x2 minus x1. So that I can write as the distance between 2 points. So it becomes 8 mu V average L upon R square. Okay. Now this is in terms of V average. If I write it in terms of discharge, so discharge is V average upon pi R square. Okay. So in terms of discharge, I can also write it as 8 mu Q L upon pi R raised to power 4. So multiply by R square, divide by R square. ठीक है, कुछ उस तरह से. Then you have to also multiply by pi. ठीक है, या आप ये कह लो कि V average की मैं वैल्यू रख दूं Q into pi R square. Okay, so this comes out to be now P1 minus P2 equal to 8 mu V average L upon R square. And in terms of discharge, it is 8 mu 8 mu QL upon pi R raised to power 4. Okay. You can also write in terms of diameter. So diameter of the pipe is 2 times R. So again, you can write P1 minus P2. This is equal to 32 mu V average into L divided by D square. Okay. Or here R raised to power 4 hai. So in terms of diameter, I can write it as 128 mu QL divided by pi W D raised to power 4. So not W. Here is only pi. So for pressure head, I divide all these terms by W. Okay, divide all these terms by W. Now these relations. There is a particular name for this relation for a circular pipe, and that are called Hagen-Postula's equation. Okay. This equation is called Hagen-Postula's equation. This is the pressure drop along a circular pipe with laminar flow. Okay. If I compare this relation with the Darcy-Weisbach equation, okay, so I can write this relation as dP by W, P1 minus P2, I write as dP by W, that is 32 mu V average L divided by W D square. So I multiply this by 2 times V average, divide by 2 times V average. Okay. Now I rearrange the terms on right hand side. So I write it as 64 divided by V average D rho. Okay. W I can write as rho G. W is rho G. Okay. So D rho divided by mu from top into L by D into V average square divided by 2G. Okay. So compare it with HF 4FL V square divided by 2GD. Okay. This is the Darcy-Weisbach equation, and this is the Hagen-Postula's equation. Okay. So from here you can see the value of 4F. So this is 4F. So this is the value of 4F. 4F as 64 divided by, now VD rho by mu is the Reynolds number. Okay. The friction factor for laminar flow through a circular pipe, the formula is 64 divided by Reynolds number. Or Darcy friction coefficient is 16 divided by Reynolds number. Okay. This is friction factor. Okay. So this is all about the laminar flow.